Welcome back to Quantum Curious. I'm thrilled to have you here for the second lecture in our quantum optics series. In our last session, we introduced the fascinating field of quantum optics, reviewed Maxwell's equations, and discussed their solutions to understand light as an electromagnetic wave. Today, we are building on that foundation to explore the energy of the electromagnetic wave. So, by the end of this lecture, you will understand how to calculate the energy of the EM field and how to normalize it according to the given constraints, and how it will relate to the energy of harmonic oscillator. So without wasting any second, we should move on to the concept of the energy of EM waves. So we know the concept of Hamiltonian, and uh, it is described as the total energy of the system. So for the case of EM waves, we can write it as the sum of the energy of electric field and magnetic field. And we also know that the energy density of the electric field and magnetic field from our elementary uh, physics classes. So we could find the Hamiltonians or energy of the EM wave by integrating the electric field and magnetic field and its energy densities over certain volume. And we could find the Hamiltonian by uh, this calculation. So our goal is to impose certain constraints on the energy and to find the energy in according to that constraint, or we can say that we want to find the Hamiltonian or energy of the EM wave in certain volume of space. And we will see that how it relates with the energy of discrete harmonic oscillators. And in the upcoming lectures, we will see that how we can quantize that uh, Hamiltonian and see the implications of the quantum nature of electromagnetic wave. So our first task is to normalize the EM field. So to simplify the task and analysis, we could assume the one-dimensional case in which we have a cavity and we have a plane wave in it, and the cavity length is L. And we have electric field propagating along z-axis, and it has polarization along the x-axis. So we could uh, write the electric field in form of it as we have spatial part and a temporal part. And our boundary conditions on the electric field is that the electric field diminishes at the perfectly reflecting surfaces. So the first boundary condition does not give any kind of meaningful results, but the second boundary condition gives us a bit of meaningful results and some physical interpretation. So after applying the second boundary condition, we could see that we have a discrete K number or discrete wave number. So it is exactly the condition on of the standing wave, and we could interpret that we have a cavity in which we have the standing waves of electromagnetic field. So in order to find the Hamiltonian of the EM wave in that cavity, we also need the other part of the electromagnetic waves, as we could see that we have magnetic field. So how can we calculate the magnetic field from the electric field given in that form? So we could use the Maxwell's equations. So we would assume here that we have a current-free region, and we would mm, we would take a derivative of time derivative of electric field, and as we know that electric magnetic field and electric field are mutually orthogonal to each other. So if the electric field is along x-axis, so magnetic field would automatically will be along the y-axis. So we have no components along x-axis and z-axis. So the curl of the magnetic field could be simplified as this form. So In that equation, we will compare the unit vectors and their coefficients. And after integrating the comparing coefficients, we get the magnitude of the magnetic field. And if we put that magnetic field and electric field in the expression of the Hamiltonian of the field that we uh, saw in the earlier slides, we get that form. So by integrating the spatial parts over certain region of space, like the cavity length, we get these results. We could easily simplify the calculations by using the double angle identities or double angle trigonometric identities. So putting these results in back into the equation 11, we get the equation 12. And we could see that it resembles to the energy of the harmonic oscillator. So if we compare the equation 12 with the exact harmonic oscillator Hamiltonian, we can get the relation between spatial parts of the actual field Hamiltonian and the Hamiltonian of the harmonic oscillator. So we have the relation between uh, these temporal parts, and here square root terms is just acting as a constant. So we could write our electric field and magnetic field in the form of variables of harmonic oscillator, and this is given in equation 14. So we could generalize these concepts or formalism into three-dimensional case, and we know that we have derived the vector potential in the previous lecture, and we could calculate the fields, the physical observables from these vector potential. So we can calculate the magnetic field from vector potential by taking it curl, and we are normalizing it in certain volume of space, in certain volume of space, where Cc is a complex conjugate. Similarly, we could write the electric field as negative of the time derivative of vector potential, and we are ignoring here the scalar potential. So we could also write the normalized form of the electric field in that form. And we should note that we have absorbed the temporal part in the amplitude to simplify the things a bit further. So again, putting the values of electric field and magnetic field in that form, and integrating over a certain volume of space, and we boils down to integrating these exponentials. So we could see that we have decoupled the modes of the EM waves, and we could write the Hamiltonian of the EM wave in real canonical variables. And real canonical variables are just like the momentum and position of the EM wave, as they are out of phase of each other. As we could give an example as that if the position or q canonical variable is varying as cosine, then momentum variable will be varying as a sine function. So we could put these values in that. By simplifying these, we could see that the Hamiltonian has this form in equation 19. And this is just precisely the Hamiltonian of discrete harmonic oscillators, where discrete harmonic oscillators are just the individual modes of the electromagnetic field. So uh, we could take this idea from our classical electromagnetic theory and try to uh, give it a quantum touch uh, by we could do it quantum mechanically by op- mm, we could do it by quantizing the magnetic field or electric field, and in results we could quantize the energy of the electromagnetic wave, and we will see these implications in the later lecture. So today we delve deeper into the energy of EM field, exploring its calculations, normalization, and relation with the energy of the harmonic oscillator. These concepts are crucial for understanding how quantum optics bridges the gap between classical and quantum physics. These principles will serve as the foundation for our future discussions, especially as we begin exploring upcoming topics in quantum optics. Thank you for joining me on this journey into quantum optics. If you enjoyed this lecture, don't forget to like the video, subscribe to Quantum Curious, and hit the bell icon to you. So